The goal for today's investigation is for you to be able to predict using an equation or a graph or maybe even a table whether or not an equation or situation is linear. And remember, a linear equation is just a special type of a proportional relationship. So you might be presented with something like this, where we've got, we're going to use those walking rates again, and we're going to think about how time walked and distance walked and how those things are related. And so if you're given a problem like this where it asks you to make a table showing the distance walked by each student, or a rate of how long or something like that, what I would suggest doing, and this is where I think it's really important to have graph paper, and I've already started this up, is get out a couple of tools like a pencil, maybe some colored pencils might be helpful, a ruler. And so what I did for this one, for Elena, Gilberto, and Leanne, is I essentially made a table that looks a little bit like this. And so now what I've got here, it gave me a clue of here, the rate right here is 1 meter per second. And so what I did is I created a column for Elena, Gilberto, and Leanne, and I thought about, okay, the time is my independent variable because it's going to go on no matter what, versus my distance is my dependent variable because it will depend on my time. And so remember that our x coordinate is our independent variable and our y coordinate is our dependent variable. And so what I went through is I said, okay, they're all going to start at the same place because they're starting at 0, 0. So when their time is 0, their distance was also 0. And then I used this information here to help me populate this table. And so since Elena has a rate of 1 meter per second, and this, let's see here, the table asked me to find how far they walk for the first 10 seconds. So I went through and I said, okay, at x equals 0, time equals 0, well, they're going to be here. And then I ran out for the first 10 seconds. And I did that for all of them. And then for Elena, it says 1 meter per second. So I know that after 1 second, she or he has traveled 1 meter. And then they're going to continue at that same rate. So at 2 seconds, they will have gone 2 meters. And again, we can think about this 1 meter per second. This is our unit rate, right? Our constant of proportionality. And that's helpful for us to think about, what did I multiply 1 by? In order to get 1, I multiplied it by 1, right? If I'm going this way, I'm multiplying straight across. We can start to notice in that pattern in the table as we move down, if our x value is increasing by the same rate every time, we can start sort of filling in some of these following that same pattern. So if I notice as I come down, every time I'm adding 1, and I'm also adding 1 here. And so Elena's is pretty straightforward. It's just going up by a rate of 1 in 1 meter as it goes over in time 1 meter. Gilberto has a similar rate, but now we've got a rate of 2 meters per second. And so again, Gilberto is starting at 0, 0. I populated my table all the way down, going up by 1 second increments because that's what the problem told me to do. And then I thought, okay, well, if at 1 second he's gone 2 meters, well, that tells me if you continue that same rate every time, I'm going to multiply whatever I have here by 2 to get to this number. And so if I'm going across, I'm multiplying times 2, right, that constant of proportionality. But I can also start noticing in my table, as I'm coming down, I'm adding 2 each time as I come down. And so I like this strategy as a way to also help you figure out like the clues in the table, and that's why I actually left Leanne's blank so we could kind of work through those ones together. So Leanne has a similar but different rate. She's got 2 meters per second. So again, starting here at 0, 0, and then at 1 second, she will have traveled 2.5 meters. And so I think, okay, what did I multiply 1 by to get to 2.5? Oh, I was multiplying by 2.5. And so I can do that same thing for 2, right? 2 times 2.5 gets me this 5. I can also, again, start noticing that in order to get from place in time 1 to place in time 2, I can add 2.5. And so as I come down, I can do this in one of 2 ways. Like I can keep adding 2.5 every time. And so at 5 seconds, I know that I will have gone 12.5, right? I can also take, if I want to multiply, 6 times 2.5 would get me that next number, which is going to be, what's that, 15? And so I can keep adding in every time. I'm just adding 2.5. What's that going to be? 20. This is going to be 22.5, and this is going to be, did I do that right? I think I did that right. I'm adding in that 2.5 every single time. Oh yeah, because then I can multiply straight across. I can double check. 10 times 2.5 gets me 25. So it doesn't matter whether you go straight across, like you're multiplying by your constant proportionality, or if you start noticing this constant rate of change. The thing you have to be careful for is to make sure that you are increasing by a constant amount in your x values. Like your x values could potentially go up by 2 or 4 or 6 or 8 or something like that. But you just want to make sure you're not like skipping numbers in there, because sometimes they'll like omit some numbers, and then you want to really think about what's my constant of proportionality. So creating a table is pretty straightforward, but I would again encourage you to use a straight edge, plotting in your x and labeling things with your x and y, so then you can, when you go to graph it, which is the next thing they're going to do, I already have my coordinates placed out for me. So remember when we graph, we always graph coordinates x, y, and so we're going to plot the x first. This is again our horizontal and or our independent variable, independent, and our y is going to come second, and that's going to be our vertical, and that's our dependent. There we go. Dependent. And so here it's going to ask me to graph the times and distance for 3 students on the same coordinate axis. And so this is again a clue. They want me to do it all on one graph. I might have had space right here at the bottom, but I didn't want things to feel squished. And so I went ahead and got a separate piece of paper. Again, graph paper is really helpful here. I've already graphed these just so I can sort of talk you through the process. You will, throughout this unit, I'm going to ask you to graph a bunch of things. So make sure you're paying attention to these mini lessons to understand how to graph things properly. So remember, our x is our horizontal, our y is our vertical. Again, x is independent, y is dependent. And if you're ever not sure like which variable is supposed to go where, like given time or distance, really ask yourself, does your time depend on your distance, or does your distance depend on your time? And start really articulating that for your brain will help you plot it out. When you create your scales, notice that these aren't the same. So like on my x-axis, I move over like 1 unit here. I marked this off, is actually represented by 2 boxes on my graph paper. And on my y-axis, it actually is 1 unit is represented by 1 box. And that's fine as long as you are consistent on your like x-axis or your y-axis. They don't have to be the same, just as long as all of one side is the same. And so then I simply went through and I started plotting my points. I started with Elena and I did 0, 0, went right there. Then for 1, 1, I went over 1 and came up 1 and plotted a point. And then for 2, 2, I did the same thing. I went over 2 and up 2. And I kind of plotted along. Again, please use a straight edge. Your lines should go through your point. There will be sometimes, these are what are called continuous, right? Continuous, because the graph continues. There might be other times where we will do a discrete graph where you just have the dots. So be careful in thinking about your data, whether it should be continuous versus discrete. This one should be continuous because Elena didn't like hop from place to place. They were like, at 1.5 seconds, they were somewhere between those 2 places. So I know I started through, in this case, I started through the origin here. This is the origin at 0, 0. And then I continued at that same rate. And so I put this arrow at the end to indicate, hey, my line is going to continue on here forever. And then I went through and I did the same thing for Gilberto and Leanne. And truthfully for Leanne, what I actually noticed as I looked at my data, because when I started graphing it, it's a little bit harder because her rate goes up at that rate of 2.5 meters per 1 second. So that was a little bit harder for me to graph, but I started noticing that like every 2, I would get a whole number. So like 2 and 5 and 4 and 10 and 6 and 15. And so that was a little bit easier for me to graph. I actually started by graphing those ones where it crossed the grid line, so it was easier for me to see. And then I went back in and I added the other ones. And like I think in here you can kind of see I almost missed one. That's okay to do because we know because it is that constant rate, it's going to continue on, and every point would sort of be on that line. And so the other part I would label on here, this would be, I want to make sure my axes are labeled. So this would be time, and this would be distance. And so now I can use this graph to help me answer some questions, right? We used in our last unit the line that has the higher constant of proportionality will have a steeper line. The word we're going to introduce in this unit is called slope. And the line that has the least steep slope has the least constant of proportionality. And so we think about writing our equations. We can use to start off that y equals kx basic format. Remember that k is our constant of proportionality. And we know from each of these, well, they gave us the constant of proportionality right here because it's that unit rate. But we can also find it on our table where the x coordinate equals 1. So sometimes they might not give it to us. Maybe they gave us some of these other coordinates and we had to work our way backwards in the table. So again, we're looking for where our x coordinate is 1. What is the resulting y value? And so my equation for Elena would just be y equals 1x. Or if I want to really put it in terms of distance and time, I can write it as d equals 1t. For Gilberto, looks like where my x coordinate is 1, my y coordinate is 2. So that equation would be that distance equals 2 times the time. And then Leanne, again, I'm looking here in my table where my x coordinate equals 1, or I can look right here on my graph where my x coordinate equals 1. And so Leanne's would be d equals 2.5 t. So again, I like using tables and graphs as a way to help me write my equation, but I can also go backwards, right? If I had this equation, I could start plugging numbers in for my t to solve for my d, to then create my ordered pairs for either my table or my graph. So it's a great way that you can connect graphs and equations and tables, as long as you know one portion of it. If you know essentially one point and one other point, you can create a graph, an equation, or a table. So big takeaways from here. These would all be proportional relationships, right? They all have that constant of proportionality. These all run through 0, 0. All of the points fall in a straight line. These are all signs I can use to predict if something is a proportional relationship. And our independent variable is our x-axis. Our dependent variable is our y-axis. And ordered pairs, we always go x, y, and in that order. And we always want to use tools like a straight edge and colored pencils to help our work be organized and neat and easy for someone else to follow.